Yeah. Okay. So in today's class, we'll be talking about week 5 lectures. So basically, lectures number 26 to 31. These are some important links that you may need. For example, the YouTube link for the sessions where they're made available, basically the YouTube link, and the Drive link containing all the materials, uh, presentations, and other code and stuff that we'll be using in the practice sessions. Mhm. Yeah, they're important links to the our website, our studio, and there's the official GitHub link for the course where all the codes for the course are stored. Uh, So we'll start with week 5, which is about correlation and regression. Before that, does anyone have any issues for previous weeks materials? Does anyone have any doubts? Okay, so we'll be continuing with week 5 lectures. So first we'll go through all the lecture materials till a point, and then we'll look at some R codes to perform regression and correlation. So just to recap, we all know that covariance between x and y basically is given as expectation of x into y minus expectation of x into expectation of y. So this basically tells us how the variable y changes with relation to x, or how does the variable x change with relation to y. So if we change the value of, if we increase or decrease the value of x or y, what happens to the other variable? If we have a sample of some sample data, so for two random variables x and y, this is how we can also calculate the covariance between them. So basically, we do summation of xi minus x bar, which is mean of x, into yi minus y bar, which is mean of y, for the corresponding pairs of x and y. We multiply them, the product, and we sum them up. Then we divide the whole thing by n minus 1. Okay, that's how we get the covariance of two random variables, x and y. Uh, we need to know, one thing to notice is that covariance basically tells you if they have a positive relation, if x and y have a positive relation or a negative relation. So for example, if you have data like this, x and y, and we have some dots like this. So basically we can see that as x is increasing, y is also increasing. So, and the covariance that we calculate for this pair of data will come out to be positive. Thus, we know that there's a positive relation between x and y. But and again, if we do that for the negative case, where we have both of them going in different directions. So when x is increasing, y is decreasing, or when y is increasing, x is decreasing. So in that case, they'll have a negative covariance. So we know that the relationship between x and y is positive or negative, but covariance does not tell us any information about how strong is the relation between the two variables x and y. And another thing to notice is that covariance depends upon the unit or scale of the variables we take. So for example, if let's say we are checking the correlation between some height and weight data. So in x-axis we have height, and in y-axis we have the weight. So if we calculate the correlation between them, it will come, the units will come to be, for x, it will be, let's say, height is centimeters, centimeters into weight is, let's say, kg. So the covariance value that we'll get is centimeter into kg. So the units will be this. So if we were to measure heights in meters or feet and inches, or measure weight in grams or something, then the value of covariance in our data will also change because it depends on these units. Okay. So thus to check the strength of relationship between two random variables, what we do is we look at the correlation between them. So basically, Sir talks about different correlation coefficients that you can calculate on data. So first one is Pearson correlation coefficient, which is denoted by a rho. So Pearson correlation coefficient is given as covariance of two random variables x and y divided by variance of x into variance of y. So standard deviation of x into standard deviation of y. As you can note here, so the covariance, let's say we again have the example of height and weight. So the covariance will have units of centimeter into kg, and our denominator here, the standard deviation will also have the units of centimeter for height and kg for weight. So all these will cancel out. So the quantity we obtain here, the Pearson correlation coefficient, is basically a unitless quantity. So this solves our second problem here, where the value dependent on the unit or scale of the variables. And the other thing is covariance allows us to quantify the strength of relation between two variables, x and y. So correlation coefficient, the Pearson correlation coefficient varies from -1 to 1. Okay, -1 to 1. And 0 is when both are random variables, x and y are independent of each other. And it is +1 in an ideal scenario when they have perfect linear correspondence. So as much as y is increasing, x is also increasing, or as much as x is increasing, y is also increasing. And -1 when they have perfect negative linear correlation. So basically, which means if x is increasing by 1 unit, y is decreasing by 1 unit. Okay. So the issue with Pearson correlation coefficient is that it's a linear correlation coefficient, so it does not capture relationships if your data has some nonlinear relationship between them. So for example, let's say we were to plot uh, x versus y, where we have y is equal to x square or something. So we have a plot like this, and we have points like this. Now, if you were to find the Pearson correlation of this data, it will turn out to be close to zero. However, we know that the data is correlated and there is some relationship between y and x, albeit it is not linear. So in those cases, we can use other rank-based correlation coefficients, such as the Spearman's rank correlation coefficient. Okay, so basically what you do in this case is, let's say you have some data x and y. Okay, 1, 1.2, 0.8, and so on, and 2, 3, and 5. So basically what you do is you calculate the rank of x and you calculate the rank of y for each variable. So for each data point. So here we first arrange everything we have in ascending order. So for x, it will be 0.8, 1, and 1.2. So the rank of 0.8 will be 1, the rank of 1 will be 2, and the rank of 1.2 will be 3. So this should be 2, this should be 3, and this should be 1. And again for y, it will be 2, 3, and 5. So the rank will be 1, 2, and 3. So it will be 1, 2, and 3. And then what we do, using these variables, rank of x and rank of y, we calculate basically using these variables, we calculate the Pearson correlation coefficient. So now we calculate the covariance between rank of x and rank of y, and we take the standard deviation of rank of x and standard deviation of rank of y in the denominator. In the Spearman rank correlation coefficient varies from -1 to 1, where 0 represents that x and y are independent, 1 means there's perfect linear relationship, and -1 means there's perfect negative linear relationship. Okay. You also talked about the Kendall rank correlation coefficient. So there's also another correlation coefficient that comes in handy if you have non-linear data or rank data. Another thing to notice is that the Spearman rank correlation coefficient can be used when the relationship between two variables is monotonic. So for example, if x is increasing, then y is increasing, or if x is increasing, then y is decreasing. But there are no changes. So this is a monotonic relationship between x and y. Okay. this is also a monotonic relationship between X and Y, because basically it's in Y is increasing as X is increasing. However, this won't be a monotonic relationship between X and Y, because like it's not monotonically increasing or decreasing. It is increasing in some parts and decreasing in some parts. Okay. So in that case, we can use Spearman's rank coefficient coefficient if the relationship between two variables is monotonic, and when we have rank data. That's when we can use Spearman's rank correlation coefficient. Okay. So coming back to Kendall rank correlation coefficient. So we have, let's say, two variables X and Y, and we have data like this, X1, Y1, X2, Y2, and so on till X and Yn. So we have n samples of both random variables X and Y. So any pair of observations, if we take X1, Y1, and Xi, Yi, and Xj, Yj. So the pair is, so we have Xi, Yi, and Xj, Yj, right? So this pair is said to be concordant. This pair is said to be concordant if uh, Xj is greater than Xi and Yj is greater than Yi simultaneously, or if Xi is greater than Xj and Yi is greater than Yj. So basically, if both of them are increasing or decreasing together, then it's called concordant. And if that is not the case, if we have the opposite thing, then it's called discordant pair. Okay. So we have all these pairs. We take all the pairs between all these their observations, and then we pair them up as then we label them as concordant pairs or discordant pairs. And then what happens? Uh, So this tau is basically Kendall's rank correlation coefficient. It is calculated as number of concordant pairs minus number of discordant pairs divided by n choose 2. So since we are basically choosing two values each time from the whole n set of data points that we are basically, so this thing is basically the total number of uh, pairs that you can get. So this is how we calculate the Kendall rank correlation coefficient. One very important thing to remember is that correlation does not imply causation. So if two variables X and Y are correlated, or have a high correlation coefficient, then the only thing that we can say about these two variables is that these two variables are correlated. So either they increase or decrease together, or if one increases, the other one decreases, depending on the correlation coefficient that you get. However, we cannot completely surely say that Y is happening because of X or X is happening because of Y. Okay, so we can't assign cause. That is the whole thing. Uh, so does anyone have any questions till now? Uh, Sorry, what is the question, Anirudh? N is sum of X and Y as in NC2 is the total number of pairs. This is basically basic permutation combination. So we have N number of data points, and at one time we are taking two data points from it. So the number of such pairs that we can take from the data is given by NC2. So N combination. Okay. If there are no more doubts, we'll move on to the demo in our regression, correlation. So first we import the data. We'll be using the iris data. So this is what the data looks like. So we have sepal length, sepal width, petal width for different flowers and the species also. Okay. So to check the correlation between two variables, so these all things will be our variables. Sepal length, sepal width, petal length, petal width will be our variables. and we want to check the correlation between them. So what we can do is we can just call this function COR So COR of, we provide the first column here, which is D dollar sepal dot length. So D is our data dollar, then we do sepal dot length, which is the heading for this variable, and then comma, and we give it the second variable D dollar petal dot length. So we want to see if this sepal length and petal length are correlated. Okay, so we'll run this. We get a variable value for correlation. We'll just print it out. So our correlation value that we get is 0.87. So basically, these two variables are um, positively correlated and they seem to have a high correlation. So what does this mean? If we visualize both the variables, so now we are basically plotting these two variables. Plot, and then we are giving the x-axis should be d dollar sepal dot length, and the y-axis should be d dollar petal dot length. If we run this, we get a plot like this. And if we zoom in, we can see that probably there's a linear relationship between both of them because as one is increasing, the other one is also increasing. Right. That's why we have a positive correlation. And the value 0.87 tells us that there is a high level of correlation between these two variables. Now, this is how we can compare, like calculate the correlation between two variables. Now, what if we were to calculate the correlation between all these variables? So what we can do is we can use the core function again, and we can provide it the whole data. So here what we are doing, call D, and inside this, the first one we are leaving blank because we want all the rows to be there. And the second one, we are just giving columns 1 to 4. So 1, 2, 3, 4, these four columns. So because these are numeric columns and we can calculate correlation between these numeric columns. So we are just giving it the first four columns, not the last one. Now, if we run this, what we get is basically a matrix. So on the diagonal, it's all one because it is the same variable. So these two variables, of course, have perfect linear relation. And rest of the values are basically the correlation coefficient for sepal width versus sepal length, if we do it, then sepal width versus petal length, and so on for different variables. And note that since correlation of x given correlation of x and y is the same as correlation of y and x, so these variables here are similar, the same. So basically, this is a square symmetric matrix. And if we see when we compared sepal length and petal length, so sepal length and petal length, we got the value, which is 0.8717, which is here. Right. So this is how you calculate the correlation matrix for the whole data. Now, by default, if you are using the core function, it will give you the uh, Pearson correlation coefficient. However, if you want to get the Spearman correlation coefficient, what you can do is you can run the code again, run the function again, COR. You give it the two variables, or you give it the whole data set, whatever you want, in case you want a matrix or you just want one value. And then in the method argument, you write Spearman. If we run this, we'll get another value for correlation, which is basically the Spearman correlation coefficient. And if we run this for the whole data set, we basically get a matrix. Again, notice that all the diagonals are 1, and it's a square symmetric matrix. Okay. So in the lecture, we were given a question. So we are given these two variables, x and y. So we are basically given values of x and values of y. So x is 0.9, y is 0.2, and 1, 0.23, and so on. We are asked to visualize the variables, both the variables, and calculate the appropriate correlation value. Okay. So to visualize, first what we need to do is we'll just plot the data. So using ggplot, what I'm doing, so I'm calling ggplot. I'm giving it data is equal to data dot frame of z. So basically, we need a data frame here. and Z is a matrix. So we are converting it to a data frame here. In aesthetics, I give it the x-axis should be the variable x and the y-axis should be the variable y. Then geom underscore point so that we get a point plot, scatter plot, and theme I'm changing to classic. If I run this, sorry, we have to first call library ggplot. Huh. So in case you haven't installed the ggplot library, you can always go to tools, install packages, and then type ggplot here, ggplot2 here, and install. Okay, I'll just run this first. So now the ggplot2 library is loaded. Now if I run this, I should get the plot. So this is how our plot looks like. So apart from this point here, the cornermost point on the right upper corner, the rest of the points seem to follow a linear line. However, we have this point in the data, and somehow it feels like there might be a better line going like this through the data. So something not linear, but slightly curved, slightly non-linear. So what we should do in this case is get the Spearman correlation coefficient. However, we'll just add a smooth line over the data. Okay. And then see if like the same thing holds. So what we are doing here, we are calling ggplot. Then we are doing geom point. So basically we want point data. And here we are providing the data frame and the aesthetics, what should be on the x-axis and the y-axis. Then we are again plotting a smooth curve over the same data. We're giving the same data and we have the same axis, right? SC is equal to false so that we don't get any confidence intervals or standard error around the line. So if I run this, we see that the line also is slightly curved. So it feels like the data is non-linear. So what uh, what is the best thing to do here would be to calculate the Spearman correlation coefficient because the Pearson correlation coefficient might not capture the relationship that we have here. So what we'll do, we'll just calculate both of them. So first here we are just calculating the Spearman correlation coefficient using COR function. So COR, we give the variables x and y. We run this and we get a correlation value of 0.9. Okay. Now what if we run the same thing with Spearman correlation coefficient? Now we run this and we see that the correlation coefficient is 0.99. So actually there might be a nonlinear relation in the data and a very strong nonlinear relation in the data that we might miss if we just calculate the uh, Pearson correlation coefficient. Okay. So given these points that we were given, after a few trial and errors, I tried to like make a nonlinear function that might be able to replicate the data kind of or fit to the data. So here basically I'm plotting the same. So this is the function log of x base 18 plus 0.24. And if we do ggplot, so basically we are plotting the point here, the points again. Then we are plotting a smooth line over it. And then we are plotting the line that we have just created the function. If you plot this, you can see that uh, you can basically remove the smooth line now. If we run this again, we see that, okay, this line maybe fits the data. So maybe the relationship is nonlinear. So the correct thing to do would be to calculate the Spearman correlation coefficient. Okay. Are there any questions regarding this? Great. Then we'll move on. Uh, yeah. So next up, we talked about linear regression. So linear regression is basically a modeling technique when we are fitting some data that we get from a experiment or some observations that we get to a linear model of the form y is equal to mx plus c. Okay. So basically y is the observation or the variable that we are measuring and x is the variable we think that has some relationship to y or is somehow related to y. Right. So to solve linear regression, we generally use the least squares method, where the aim is to minimize the sum square of residuals or the residual sum square, so SSR or RSS, which is given by yi minus yi hat whole square sum. So basically, yi is the observation or so we have a table like this for our data, x and y. We'll have values 0 0.1, 0.3 and so on, and 1, 2, 7 and so on. We'll have values. So basically, what we do is to solve linear regression, what we do is we assume a line. So we assume the values for M and C initially, and then we calculate this, which is basically yi hat or y hat here will be given the values of M and C or slope and intercept. What is the value of y that I expect here given this x value? So basically, this will be mxi plus c. So in this case, it will be m into 0.1 plus c. In this case, it will be m into 0.2 into c, m into 0.3 into c, and so on. So we'll sum all these values, the whole column, and then what we'll try to do is we try to minimize this. So we are trying to minimize the residual sum of squares or the errors. Okay. Uh, so the best fit line will have the least value among uh, least value for this RSS or SSR. So that best fit line, if you solve using mathematics, what you get is the slope of the best fit line should be covariance of x and y divided by variance of x. And the value of c you can calculate from the equation mean of y minus slope into mean of x. Okay. So if we reformulate the whole question, so what we have basically is we have some equation of the form y is equal to mx plus c, right? So for each of these points that we have, x1, y1, y2, x2, x3, y3, and so on, what we have is this equation should hold. So basically y3 will be equal to mx3 plus c. Y2 will be equal to mx2 plus c. Y1 will be equal to mx1 plus c. So we can reformulate this whole thing in linear algebra terms as a matrix multiplication problem. So basically we have a y matrix here, y3, y2, y1, which is given by this X matrix, which is basically x3, x2, uh, x1, and 1, 1, 1. And here we have M and C. So this is our M matrix. So this is Y, this is X, and this is M. So when we multiply, what we are doing is we basically get back the equation. So x3 into m plus 1 into c is equal to y3. So mx3 plus c is equal to y3. So the solution to this in linear algebra terms is given as m is equal to x transpose x inverse into x transpose y. So this is the solution if you solve it using linear algebra. So generally, when we are using R and everything, it's much easier computationally to solve these problems using linear algebra. That's why we'll be using this form in the backend. Right. So in multiple linear regression, what happens is basically, so this was simple linear regression where we have two variables, x and y. Okay, we want to predict y given the values of x. Now, in multiple linear regression, what we want to do is we have a lot of different variables, x1, x2, x3, and so on till xn, and then we have y. So basically these x1, x2, x3, all these are our predictor variables, and y is our target variable, the variable we are trying to predict. Okay. And these are all our predictor variables or our features. So here also, in the case of multiple linear regression, I can make a regression equation, so which is basically given as y is equal to b1 x1 plus b2 x2 plus dot 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 bk xk plus a. So the a here is our intercept, and bk, b1, b2 are all our coefficients for each of these variables, depending on how important they are to predict y, right? Or like how do these values combine to give the value of y? Hmm. Here again, what we are doing is we can try to find a solution by using the least square method, where we just basically predict all these, find the coefficients b1, b2, bk till bk and a, whichever coefficient gives us the minimum value of SSR or RSS, so residual sum of squares. This whole thing is basically the line that fits the best. Okay. Again, if you formulate the question in linear algebra terms, we'll again, instead of this, what we'll have is a bigger matrix. So we'll have a y matrix given by y1, y2, dot, 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 till yk, which is given as, uh, sorry, which is given as, basically we have a matrix x1, 1, x1, 2, x1, k, y1, y, sorry, 2, 1, y2, 2, y2k until, sorry, this will all again be x till xn1, xn2 till xnk. So we have this matrix, which is our x matrix, and we have another matrix, which is basically b1, b2 till bk, and then a, our intercept. And this matrix again has ones at the end, a row, a column of ones. So this is how it turns out to be. So this will be our B matrix now. This is how it turns out to be in multiple linear regression if we do it in linear algebra terms. So here again, the solution that we get is basically x transpose x, inverse of that into x transpose y. Okay. So there's one problem in multiple linear regression that does not arise in simple linear regression, which is the problem of multicollinearity. Okay. So we talked that the linear algebra solution for this is B is given as this, right? So we have the term x transpose x, which we need to invert. So basically our x transpose x matrix needs to be invertible, or it should be a full rank matrix. Okay. So the rank needs to be full. It should be the number of columns or rows that it has. So this can only happen if the matrix X is like all the columns and rows of X are linearly independent. That is, you cannot, so for the X matrix, what we had was x11, x12, and so on, x1k, then xn1, xn2 till xnk, right? And 1, 1, 1, 1, 1. So basically, all of the rows and all of the rows and all of the columns of this matrix need to be linearly independent. So we cannot get a single column by doing some linear modification or multiplication or division or linear combination of the other rows that we other columns that we have here. Okay. So that's something that we need to take care of in linear, multiple linear regression. Otherwise, we might not get a solution to our problem, or we might get a false solution, or the statistic that we calculate later might be uh, erroneous, right? So how can we detect multicollinearity in data? So one thing we can do is we can check the pairwise correlation coefficient between all these columns or all these predictor values. So we take two at a time, and then we basically calculate the correlation value and see if it's high or low. Another thing that we can do is we can calculate the variance inflection factor for each of these columns or each of these predictors. So basically, what does variance inflation factor, what is it and how, what does it do? So we have different regressions, auxiliary regressions for each of these independent variables. So basically, we'll have equations such as xj is equal to uh, b1 x1 plus b2 x2 plus dot 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 uh, b j minus 1 x j minus 1 plus b j plus 1 x j plus 1 and plus so on till b k j k x k. Okay. So basically what we are doing is we are trying to build a regression model for this variable. We are taking this variable out of here and we are using all the other variables to basically predict the value of this variable. Okay. So we are basically doing a regression for this. Uh, in each of these cases, for each of these variables, x1, x2, x3 till xk, till xn, sorry, so this will be n, till xn, all of those variables. In all the cases, we'll calculate the R square value and the variance inflation factor for a given predictor xj is given as 1 by 1 minus R square of that uh, corresponding auxiliary regression that we carry out. Okay. So let's see what happens here. So let's say in this regression, we get a very high R square value. Okay. So we have this equation 1 minus 1 by R square. So this R square value is high. So this 1 minus R square value is very so this R square value is very high. When we subtract 1 minus this, the denominator will be so the R square value will range from 0 to 1, right? R square basically ranges from 0 to 1. So the correlation. So basically, if it's close to 1, the thing that we get here will be 0. And since we are dividing 1 by a very low number or 0 or close to 0, we'll get a high variance inflation factor. Now, if R square is less, we'll subtract less from the denominator. Our denominator will be bigger and we'll get a smaller value. So if R square is high or if this variable has some relation with uh, other variables or combination of other variables, we'll get a high VIF, and thus we know that this particular feature or predictor in question is related linearly dependent on other predictors that we have. So it's better to remove it. So basically, if you get a VIF of higher than greater than 10, you generally discard the predictor variable that you have. Okay. So how do we handle multicollinearity in the real world? So the first thing would be to design experiments such that you are choosing variables that are most likely not related or not linearly dependent on each other. That's the best thing to do. Okay. In case you are not able to avoid it and you need a lot of variables to build your model, if you are just using your model to make predictions within the range of the data that you have of X and Y, then it is okay to still use the model. So you can basically tolerate a little bit of multicollinearity in this case because you are just making predictions and that too within the data range of the predictor. So within the maximum and minimum of the predictor variables, you have some other uh, thing that you want to predict. However, if you are using the regression to state a relation or to like basically test for causation or do more experiments, the best thing to do in that case would be to remove the uh, variables. So basically, if a variable has a high VIF, which is generally greater than 10, you remove the variable from your experiment or from your analysis data set for regression. Okay. Uh, is everything clear till now? Does anyone have any questions? Okay, great. So next we talked about some diagnostic checks that you can do for linear regression to see if basically your regression is good enough or you need to do it again, or like if you can basically depend on the coefficients, the way values of the coefficients that you have. So for that, what we check is basically called the coefficient of determination or the R square. Okay. So R square basically compares how good is a given linear regression model compared to the worst model that we can think of. And the worst model that we can think of in general is the mean model. So basically, where we assume that there is no relationship between x and y, and all the y values should have been a constant value, but there is some variation due to some experimental error or something. So in that case, R square is given by 1 minus RSS by TSS, which is a residual sum of squares minus divided by total sum of squares. So residual sum of squares is again given by y minus the predicted value of y at the given x whole square, sum of that. And total sum of squares is given by y minus the mean of y, square of that, and sum of all y values. Okay. So our R square value here basically varies from 0 to 1. So if you get a R square value of 0, your model is performing as bad as the mean model or the worst model in this case. However, if you have a R square value of 1, your model is basically perfectly fitting to the data. Okay. Mm. So this is in the case of uh, generally simple linear regression we use. In case of multiple linear regression, what we do is we use something called adjusted R square. So basically what happens in multiple linear regression is that if you keep adding more variables to the data set, the predictions that you make generally are either the same or better. So basically the R square value that you will get by adding different more predictor variables will be either uh, same to the previous model without the new variable or better than that. So basically, if you add new variables, your R square tends to increase. So in case of multiple linear regression, what we look at is adjusted R square, which basically penalizes the R square if the number of model parameters that we have or the number of predictor variables that we have increases. So this adjusted R square is denoted as such and is given by 1 minus RSS by TSS. Again, RSS and TSS are given here, multiplied by n minus 1 divided by n minus k minus 1, where n is the number of data points we have and k is the number of predictor variables or the number of x variables or parameters that we have. Okay, so this is the first thing you should do to check if your how good is your model compared to the worst model. So if you get a high R square value for your model, that means your model is pretty good given the data. Okay. And you should keep it. If you get a low R square value, then probably you need to change some things. Right. So before we move into the next diagnostic check, what we'll do is we'll basically recap a few things. So the first thing is the concept of statistical test. So basically, what we have in when we do an experiment in a lab or we collect data from outside, what we basically have is a sample. So this is our basically population. And in lab and all environments, what we get is basically a sample, which is basically some handpicked values from the population, right? So let's say you were to measure the height and weight of 10, 15 students in a class, then the height and weight of these 10, 15 students will be the sample, whereas your population might be the students of that class or the students of the whole school, right? So in general, when we are doing some experiment, we generally know or observe values for a sample, but we want to generalize the whole thing to a population. Okay. So we can do that by using statistical tests. So basically, in a statistical test, we are comparing distributions of populations. So we have sample data, but we want to know if about the population, what is happening in a population. So let's say we have two samples, S1 and S2. We want to see if they come from the same population P1, or they come from different populations P1 and P2. So in the case of statistical test, what we have is a null hypothesis and an alternative hypothesis. A null hypothesis is basically a statement of no effect, or basically uh, as the assumption that generally everything is same or everything is zero. So in this case, what will be our null hypothesis? It will be that both the population distributions are the same. So P1 is equal to P2. And our alternate hypothesis will be P1 is not equal to P2. Okay. So we have some population. We are given two samples, which might be drawn from the same population or different population. Now, using statistical test, the question that we want to answer is, if two population distributions are the same, then what is the probability that the difference between the sample means that I get must be greater than or equal to the observed difference of sample means. So for example, assuming that both these samples come from the same distribution, the difference of means that I get from these samples, how likely it is to occur if I repeat the experiment or if I take a large number of samples. Okay. So basically, that is that. Then to compare the two populations or distributions, what we do is we do have some statistic for the test. So different tests will have different statistic that they test, and they'll be checking between different things. So if the means of the populations are the same, or if the variance of the populations are the same, and stuff like that. And basically, once you have a statistic, you calculate the statistic for your given samples, and then you compare it to a suitable probability distribution to test if your results are significant enough, if the value that you're getting is high enough, so that you can basically reject your null hypothesis and say that both these samples maybe come from different populations. Okay, was that clear? Great. So we'll again recap the t-test. So t-test is basically a statistical test that is used to compare the sample means of two distributions. So in our null hypothesis here, we have that the population means, population 1 and population 2, mu1 and mu2 are the same. And the alternative hypothesis, we have mu1 and mu2 are not the same. And we have some samples, x1 and x2, that we are given. We want to check if both of them come from the same population or not. So the T statistic is given as sample statistics minus population parameter divided by standard error of sample statistics. That's how the T statistic is defined. So basically, sample statistics is mean of x1 minus mean of x2, where x1 and x2 are our samples that we have given, and the population parameters are mu1 and mu2. So this T statistics we calculate under the null hypothesis, where we are assuming that mu1 is equal to mu2. So mu1 minus mu2 will be equal to 0. So we are eliminating that here. And the standard error of the samples is given as 1 by n1 plus 1 by n2 into standard deviation square. So n1 and n2 are basically the number of data points in x1, number of data points in x2. Right. So this T statistic conveniently follows a distribution called the T distribution with degrees. So degrees of freedom. n1 plus n2 minus 2, where n1 and n2 are basically number of samples in x1, number of samples in x2. So once we have some sample x1 and x2, what we do is for each of the data points, we calculate these t statistic for the whole data. Then what we do is we compare the t statistic to the t distribution and see what is the probability of us observing this value, given that both the distributions are the same. And then if the value that we get, the t value that we get, the t statistic value, is greater than the value that is the t value for our basically alpha level or the level of significance. So level of significance is basically the some level of significance that you have thought about before doing your experiment. So in general, people put a 5% level of significance or a 0.05 level of significance, where you accept the fact that 5% of the times you might be wrong, but 95% of the times you are right if you are rejecting the null hypothesis. Okay. So basically that's it. Then what you do is you compare if your t value is greater than the t value for this level of significance. And then what you do, if it is greater, then you reject your null hypothesis. If it is lesser, then you accept your null hypothesis. So if, let's say we do this calculation for our samples and we find that the t value that we obtain is greater than the t value for the uh, level of significance 0.05 that we want to check, then what we can say is we can reject the null hypothesis, or we say that the means of the populations are different, or these two samples come from different populations. Okay. So that is basically what we try to do in a t-test. Is that clear? Great. So the second diagnostic check for linear regression is to check if the coefficients that we have got in the linear regression are basically the coefficients of the population, or does the population also have a linear relation? So let's say we found a linear relation between our sample x and y. Does the population also have the same linear relation? So that is basically what we are testing here. So when we are doing a statistical test. So in this case, our null hypothesis is that beta is equal to beta naught or 0. So beta is our population parameter. Our alternative hypothesis is that beta is not equal to 0. So our alternative hypothesis is that there is a population relation between x and y in the population. So basically the population relation is given as y is equal to beta x plus alpha or something. So the alternative hypothesis is that beta is not equal to 0. There is some linear relationship between y and x. Okay. So to prove this, to check this, what we do is for each of the coefficients and the intercept, we calculate the t statistic, which is given as b minus beta naught by sample variance of b. So for the sample, we have the equation y is equal to bx plus a. This is for sample and this is for populations. Okay. Mm. So what we do is for each of the coefficients that we have in our regression, we check if it is significant or not. We also check if the intercept is significant or not. And if we find that some of the coefficients or intercept are not significant, what we do is we basically repeat the regression without that specific coefficient. Okay. So in case of multiple linear regression, there's one more question that we can ask. In case of multiple linear regression also we can, so this thing we can do for both simple and multiple linear regression, where we are basically for each of the coefficient we are checking a t statistic, we are calculating a t statistic and seeing if it's significant. For multiple linear regression, an additional thing that we can do is basically we can ask the question, is the model with several predictors better than a model without any predictors to capture the linear relation? So basically here what we are doing, our null hypothesis is that all our population coefficients are 0. And our alternate hypothesis is that at least one of the coefficients is not 0. So at least one of the variables is related to the y value that we are trying to predict. So this multiple linear regression, this thing is checked using a F statistic. So we calculate a F test statistic for the whole thing, where the F statistic is given as summation of y hat minus yi mean. So basically predicted value of y minus mean of y whole square, sum all of it across y. And then on the denominator, we have yi minus yi hat whole square, sum of it. So basically, this is our RSS and this is our ESS, or error sum of squares. How much explained sum of squares? So how much of the error is explained by the model divided by how much is the error that is not explained, or the residual error. Okay. Then we multiply this by n minus k minus 1 divided by k, where k is the number of variables and n is the number of data points that we have. Okay, so these are the tests. And in F statistic, the test what we are doing, if we basically get a value which is greater than the F statistic at our level of significance, what we are basically saying is at least one of these coefficients has some relation with the variable that we are trying to predict. Okay, we don't know which one, but at least one of them. The other thing that we can do for linear regression is we can calculate what is called a confidence interval for the regression coefficients. So basically, we have a sample and we have some sample parameters, B and SV. So basically, B is the sample coefficient and SV is the sample variance. And what we want to do now is we want to, given this sample regression, this value B, we want to figure out where does the population value lie. So in the population regression equation that we have here, so we have this B, we fit our data to our sample, but we want to know what is the value of this beta that we have in the population level. So what we can do is, using confidence interval, what we do is we can calculate beta as such. Beta is given by B plus minus T alpha by 2, where alpha is our level of significance that we are checking at. So if we are checking at level of significance of 95% or 90%, the T alpha by 2 value will change. And SB is the sample variance. Okay. So basically, what we have here is we are here B, and we are saying B plus T alpha by 2 SB and B minus T alpha by 2 SB our true population parameter, that is beta, will lie somewhere between these with a level of confidence that is equal to the level of significance. So with 95% confidence, we can say that if we have all the population data, the beta value will lie within this range. That is all that we are saying when we are using confidence intervals. Okay, is that clear? Does anyone have any questions? Great. So we'll move on to the R studio. So here, uh, in the lecture, the regression lecture, we were given a question. Uh, G1 is given as this and G2 is given as this. So what we'll do is we'll first make a data frame. So we'll look at the data frame. So G1, we are given some variable values. G2, we are given some values. So the question is, we have to do regression using means, variances, and covariances for the data. Sorry. So basically, we have an equation here, right? We are doing simple linear regression because we have two variables. We have an equation here. M is given as covariance of X by variance of Y, and C is given as this. So we are basically asked to use these formulas to calculate the regression coefficients M and C for the data X and Y that we are given. Okay. So we'll first view the data frame. So this is G1 and this is G2. So we'll make a note of what we need to calculate. So we need to calculate the covariance of X and Y, and we need to calculate the variance of X. Okay. Remember that the covariance of X and Y is given as sum of Xi minus X mean into Yi minus Y mean. The across all the products, we take the sum. So basically, we need Xi minus X mean. So first, we need to calculate the mean of X. That's what we are doing in the second line. We are taking the mean of G1, data frame dollar $G1. Then we are creating a column called G1 difference, where we are storing the value of X minus mean of X. So value of G1 minus mean of G1. So GI minus mean of whole GI. So this is basically we are subtracting from the column all the mean value. We run this and we check the data frame again. So now we have a data frame called G1 diff. We'll check the mean value. So mean of G1 is 1.97. Now what we are doing here is 1.25 minus 1.97, which is basically minus 0.72, 1.32 minus 1.97, which is basically minus 0.65, and so on. We have. Okay. Then what we do to calculate the variance, what we need to do is we need to take the square of this difference and sum it up. So basically here we have X minus mean of X. So G1 minus mean of G1 whole square. We are creating a column called G1 difference square. So basically we have G1 difference here, which is basically G1 minus the mean of G1. And what we are doing in G1 difference square is we are basically squaring this term. So we are taking this G1 diff and we are squaring it, raising it to the power of 2. Now when we do this, we have another column G1 difference square. So it's basically the square of these values. Okay. Similarly for Y, for G2, we calculate the mean by using the mean function. Then we calculate G2 minus mean of G2. We create another column G2 diff, which is given as G2 minus G2 mean. We have G2 diff here, which is basically 2.25 minus G2 mean is somewhere 3.29. So 2.25 minus 3.29, which is minus 1.044, 2.5 minus 3.29, which is minus 0.79, and so on. Okay. Then what we need to do, we'll take a look at the formula again. So basically, it's covariance of X and Y divided by variance of X. So covariance of X and Y, we can calculate like this. Variance of X is basically Xi minus X bar whole square divided by N minus 1. So if we divide these two terms, the N minus 1 cancels out. So for example, if I were to write this whole thing, expand it out, what will it be? Xi minus X bar into Yi minus Y bar summation of this divided by N minus 1 into sorry, we are calculating this basically, not the other one. This one we are calculating. So again, sorry for the confusion. So M is given as Xi minus X bar, Yi minus Y bar summation divided by Xi minus X bar whole square summation. So this will be our N, because this numerator term has a N minus 1, this denominator term has a N minus 1, and these two things will cancel out. So we'll just have this. So now we have rho for the value of Xi minus X mean, we have a rho for the value of Yi minus Y mean, and we have a rho for the value of Xi minus X mean whole square. So what we can do is just basically multiply these two rows, sum it up, and divide it up by sum of this row. Sorry, this column basically. So we have a column G1 diff, which is basically G1 minus mean of G1. We have G2 diff, which is G2 minus mean of G2. We'll multiply these two columns. Then we'll sum the whole thing. Then what we'll do, we'll take this G1 difference square and we'll sum it up. And that will be our denominator. The previous thing will be our numerator. So this is what is written here. X minus X mean into Y minus 1 Y mean. We multiply these two columns. So this is what we are doing here. df dollars G1 underscore diff. We are multiplying this column by df dollar G2 underscore diff. So this is basically element wise multiply the values of G1 diff and G2 diff. Then we are taking the sum of the whole thing. That will be our numerator. The whole thing we are dividing it by the sum of G1 difference whole square. So basically, G1 minus mean of G1 whole square. We are taking the sum. So this is basically the variance, and the numerator term here is basically the covariance. Now, if we run this, we get a value of M, which is 1.44. Then C, we can easily calculate using the equation here. C is given as mean of Y minus M into mean of X. So Y here is G2. So mean of G2 minus M into mean of G1. We calculate C. So basically, that's all. We got the value of M, which is 1.44. We got the value of C, which is 0.44. And then what we are doing here is we are making our the predicted points for our line. So basically, we store it into a variable called y prime, where what we are doing, we are taking the x values or G1 values, we are multiplying it by M, and we are adding C. So for each point of G1, we are trying to see in the y prime column, what is the predicted value of G2. So we can write it as, we have written it as y prime. So this basically, given this G1 value, and our values of slope and intercept, we should get this point here. And given this value of G1, we should get G2 value, which should be this, and so on. So now we are basically plotting the data. So we are making a point data where we are using the data frame DF, the mean data frame. And in the aesthetics, we say on the x-axis plot G1, on the y-axis plot G2. Then we are also plotting a line where we are providing the same data. However, we are in the x-axis, we have G1, and in the y-axis, we have the predicted line that we have. Okay, the linear regression line, the fitted line that we have. If we run this code, we see that we get all the points, and the line for our linear regression plot is also plotted. And it feels like the line is basically uh, passing through all the points. So probably the best fit line, right? And mathematically, we can say it is the best fit line. Does anyone have any doubts with this? Okay, great. So we'll move on to the next code. So basically, this is regarding simple linear regression using where we are creating a linear model of the form y is equal to a plus bx, where x is our independent variable or predictor and y is our dependent variable or response. So this is an example using R. So basically, we are reading some data that we have, blood pressure data. So it has two columns and around 30 rows. So 30 samples and two columns, two variables. One is age and one is uh, systolic blood pressure, upper one. Okay. We can use the plot function where we are giving basically a age for the x-axis, systolic blood pressure for the y-axis. We are giving it the x label age, the y label systolic BP. We are giving it a color red, and we want the points to be like this. PCH is equal to 1 basically defines the design, and CX will basically produce a bigger point. So CX equal to 2 will produce bigger points. 1 stands for a hollowed out circle. Right. Now we see that apart from this one outlier here or one high point here, rest of the data seems to follow a linear regression or a straight line. So we can say that the systolic blood pressure depends on the age somehow or is correlated to the age somehow. So what we want to do is we want to put a linear regression model through it. We want to draw a best fit line through all these data points. So what we are doing here is we are basically calculating the Pearson's correlation coefficient to see what is the correlation between these two variables. So we are providing D dollar age and D dollar systolic BP, and we want the Pearson correlation. So we run this, we see that the correlation is 0.65, which is slightly high. So there might be some linear relation. So what we are doing here is basically doing a linear regression or fitting a linear model using R. So basically, to this LM command, the linear model command, what we are saying, take the systolic BP that we have in our data set, sys.bp, to be the dependent or the response variable, and the age to be the predictor or the independent variable. And we are giving the data equal to D, that we read here. Okay. So we do this, we store the result into a variable called reg. Then what we do, we call summary of this variable reg. So what does the summary give us? So the summary gives us what formula was used. Okay. It gives us all the residuals, and then it gives us the coefficients. So the intercept is basically the intercept of the linear model. So y is equal to mx plus c. This intercept is c, and m here is the slope. So this h thing here is the slope. So this thing here is the m. So R basically calculates all these, estimates the standard error in all these, and calculates a t value and gives us a probability. Since we have 3 stars in both cases, we know that the coefficients are significant at a 0.001 level also. So basically, it's good enough for us. Then what R also gives us is the multiple R square, which is basically the R square value. So we see the R square value is 0.43, so which is not that high. Okay. Uh, that doesn't matter, but still there's some positive correlation, positive relation between them. And yeah, that's all we need to look at here for this simple linear regression. We can use the R function conf int and we give it a level of significance, let's say 0.95 or 95% significance. We give it the reg, which is the linear regression that we carried out here. So basically reg, comma, level is equal to the level of significance. And if we run this, we see that we get the uh, basically the confidence intervals for our intercept and age. So the population age slope should vary somewhere between coefficient for age should vary from somewhere between 0.5 to 1.4 with 95% certainty. And the intercept should vary somewhere between 78 to 119 within 95% certainty. Okay. Now here what we are doing, we have the plot. We are just using AB line to draw line. Okay. Overlay the regression line that we have. So we are giving it the model here, regression that we had. The color we want blue, we want the line to be blue color, and LWD is basically the width of the line, which is 2. If we run this here, and we zoom in, we see that our model basically fits the data really good, and we see a regression line passing through the points that we have. Does anyone have any questions or issues? Okay, great. So we'll move on to the next one. So here again, we are doing linear regression. So we are reading some data, DNA data, which has basically 7 samples. And we have 2 columns, concentration and absorbance. So it's some absorbance data, DNA absorbance data. we'll basically plot it first. So what we are doing, we are giving the DNA dollar concentration for the x-axis, DNA dollar absorbance for the y-axis, the x label, the y label, and the color. PCH is basically how we want the points to look, and TX is basically the size. We run this, we get this plot. We see that maybe there's some linear regression between these two variables. So it seems like they are increasing together or decreasing together. So what we'll try to do, we'll try to fit a default model, which is y is equal to a plus bx. So what we are doing here, we are calling linear model. We are giving it absorbance as the dependent variable, the one on the y-axis, and concentration as the independent variable. And the data is the DNA data that we have read. Now we run this and we check the summary. We see that there's a formula. We get the estimate of the intercept and the slope. We see that our slope is basically significant at 0.001. However, our intercept is not significant at the level of 0.05, which is the level that we want it to be. So what we'll do is we'll basically remove the intercept and run the regression again. So this follows from basic theory that in when we observe absorbance, absorbance is given by A is equal to E some constant into L, which is the path length into the concentration at lower concentrations, low enough concentrations. Okay. So this is this is called Beer-Lambus law, and this does not have an intercept. So the line that we should expect in this case also should not have an intercept theoretically. And that is what we get when we run our model with an intercept. We see that the intercept is not significant. So what we do, we remove the intercept and try again. So how can we do that? So we are creating another variable R2, which is again a linear model. So ABS is basically the absorbance, which is a dependent variable. Concentration is our independent variable. We have a tilde here, which signifies relation. And here we have a plus 0, so that we write a plus 0 so that R knows not to fit a intercept. So plus 0 means don't fit an intercept here. And then data is given as the DNA data, right? Now we run this, get the summary, and we see that we just have one coefficient concentration. We have a slope value here, and it is significant. We check the R square, which is 0.98, which is very good. And then what we do, we see, we just basically plot the regression line on top of it. So we again use AB line. We are giving it the linear model, the result what we stored. We are giving the color blue and the line width as 2. We run this, we see, we get a line which basically fits the points. Okay. Is that clear? Okay. So someone has a doubt, when will our exam be held? So you can ask questions like this in the discussion forum. I think it's more appropriate there. Anything related to the exam and what you might have in the exam, or uh, when it will be and how it will be, you can ask on the discussion forum. Okay. Okay. Does anyone have any doubts here? Good. So we'll move on to the next uh, one, next week lectures. So here we are basically doing multiple linear regression. So our problem is that create a linear model to represent the length of the fish as a function of age, which is the age of the fish or the number of days it has been alive, and the temperature of the water. So basically, this will be our linear model. Length is given as B1 into age plus B2 into temperature. So what we'll do is we'll basically first read the data. Then we are basically fitting a regression model. So we'll first take a look at the data. This is how it looks like. We have age, we have temperature, and we have the length of the fish for 44 fishes. Okay. To perform this regression, what we do is regression is given as linear model. Length is the value that we are trying to predict, the target variable. tilde, and we have all of our variables that we are using as predictor variables here. So age plus temperature plus 0 because we don't want to fit any intercept here. And data is basically the fish data that I've read here. So we do this, and then we check the summary. So the summary of this regression basically gives us a lot of things. We have the coefficient for age, we have the coefficient for temperature, we have the t-test t-value and the probability. We see that both of these are significant. Okay. Here we have the adjusted R square, which is 0.96, which tells us that the fit is good. And we also have, in the case of multiple linear regression, we have the F statistic that we can look at. So the p-value that we are getting is less than 2.2 raised to power minus 16, 10 to the power minus 16, so which is basically very low. So we know that our model is significant. Okay, so this t-test is the F-test, the ANOVA thing that we did basically. So that's all that we get from here. And the confident function basically gives us the confidence interval. So if we run confident and we give it the regression model that we have fitted here, it will basically give us the confidence interval for all of our variables, all of our predictor variables. So age, the coefficient, population coefficient should lie between 22.69 to 31.88 at a 95 level, 95% level of significance. So by default, it takes a 95% level of significance. Again, for temperature, the same thing. Our population statistics should, population parameter should lie between 13.7 and 44.4. Okay, is this clear? Does anyone have any questions? Great. We'll move on to the last one. So here is another example of multiple linear regression. We are basically reading a data set. We have four columns here and multiple rows, 45 entries, 45 rows and four columns. These all are our variables. Okay. So what we are trying to do is S will be our response variable, and we are trying to predict the value of S given the value of M, P, and R. So here what we are doing, we are calling linear model. We are saying that S is the dependent variable. We are giving a tilde and then we give a dot. So a dot basically means take everything else that is there in the data set as a predictor variable. And data we are providing as this the data set that we read. So we'll run this and we'll check the summary. So this is what we get. So we get for M, P, and R, what are the estimates of the coefficients. For intercept, we get what is the estimate of the intercept. Since we did not say that don't have an intercept here, plus 0 we didn't write, we have an intercept here. We see the t values for all of them. For this p variable, we have a slightly less significant p-value, which is still significant at 0.05. So all our variables are significant as 0.05. Then we have our adjusted R square of 0.59, which is good enough. It's around zero 0.6. Then we have a p-value here for the F statistic. So this p-value is also very less compared to 0.05. So we know that our model is good. Okay. Next, we check for how we can handle multicollinearity and all. So let's say this data looks good, but what if it has some multicollinearity? We need to check for that. So there's a library called CAR, which has a function called VIF, which basically calculates the variance inflation factor for each of our predictor variables. So if we run this, we load the library CAR, then we run VIF of regression.multi, which is the variable we stored our model in. So if we run this, we get for M, the VIF is 1.6, for P, it's 1.6, for R, it's 1.14. So basically, none of these are that significantly high. None of these are higher than 10. So we don't need to remove any of these. However, if we were to find that if one of these were greater than 10, then we would need to worry and we need to modify our model accordingly. Is this clear? Does anyone have any questions? Okay, great. So we'll just move back to the slides. We have a few practice questions. So the first question is, which of the following represents Pearson correlation coefficient between two variables, A and B? So if we remember correctly, we have the variables A and B. The Pearson correlation coefficient is given by covariance of A and B divided by standard deviation of A into standard deviation of B. So rho is given by this. So which is option A here. So the answer here will be option A. Okay. Calculate the Pearson's correlation coefficient between X and Y using the following data. Okay. So we have the data. Let's write it down. So we have X and Y. We have 2, 5, 5.5, 1, 2, 3. Okay. So to calculate the Pearson correlation coefficient, we'll do it by hand because in the exam you won't be given R to depend on. You will be given a calculator. So this you need to calculate all these things by hand. So that's what we'll do now. So first, what we'll do to calculate the rho, what we need is covariance of X and Y divided by sigma, this thing, right? Sigma of X into sigma of Y, right? So to calculate covariance of X and Y, what we need basically is xy minus x bar into yi minus y bar summation of this divided by xi minus x bar whole square root over into yi minus y bar whole square root over. So this is basically standard deviation of X and standard deviation of Y. So all of these, like again, like previous, so this thing is divided by n minus 1. This thing is divided by root n minus 1. This is divided by root n minus 1. So these things cancel out. So at the end, we have these things. So what we need here is, we need xi minus x bar. We need xi minus xi bar whole square. We need yi minus y bar. We need yi minus yi bar, y bar whole square. And we need x1, xi minus x bar into yi minus y bar. So these are the columns that we'll need. So what we'll do, we'll calculate all of these. So first we'll calculate the mean of x. So x bar is given as 2 plus 5 plus 5.5 divided by 3, which turns out to be 25 or 12.5 divided by 3, which turns out to be somewhere around 4.1667. And y bar again we have as 1 plus 2 plus 3 divided by 3 is basically 6 by 3, which is 2. Okay. So this xi minus x bar will be 2 minus 4.1667, which is minus 2.1667. This one will be 0.8333. 5 minus 4.1667. There's 5.5 minus 4.1667, which is 1.3333. Okay. Then here what we'll do, we'll basically square these three things. So square of this will be 4.6946. Square of this will be 0.6944. And square of this will be 1.7777. Okay. Then we need yi minus y bar. So 1 minus 2, which is minus 1, 2 minus 2, which is 0, and 3 minus 2, which is 1. we need yi minus y bar whole square, which is basically 1 here, 0 here, 1 here, square of these. And this is basically this one multiplied by this one. So here we have minus 4.6946. Here we have 0. And here we have 1.3333. Okay. So now what we need the, okay, there's also a sum here, there's also a sum here. So what we need is we need the sum of this column, the sum of this column, and the sum of this column. So we'll calculate the sum. So this one will be around 7.1667. This one will be 2, and this one will be, okay, 1 sec. This is xi minus x bar into yi minus y bar. Oh, this is minus 2 point thing into this. So this will be actually 2.1667. Okay, so now if we add all these values, we get 3.5. Basically, this is our total for this column, this is our total for this column, this is our total for this column. Now what we need to do, we need to put these values here. So basically, here we have 3.5 divided by root over of 2 into root over of 7.1667. If you use a calculator and calculate this, the answer will be 0.5 by 0.7859, which is approximately equal to 0.924. So this will be our correlation coefficient, Pearson correlation coefficient. Does anyone have any issues with this? Okay, great. We'll move on to the next question. Which of the following coefficients of determination value indicates a good fit for a linear equation to data? So coefficient of determination is basically our R square. It varies from 0 to 1, where 0 is the worst and 1 is the best. So the value can't be negative here. 0.1 is not a good value. 0.32 is not a good value. 0.89 is a good value. So the answer here will be this. Okay. Is that clear? Great. Which of the following is used to measure the goodness of fit in multiple linear regression? So in multiple linear regression, to check the goodness of fit, instead of R square, we use the adjusted R square. Okay. Straightforward. Next question is, we have a multiple linear regression model. Y is equal to bx plus dz plus kw plus a. Here b, d, k, and a are the population model coefficients. Which of the following is the correct null hypothesis for the ANOVA of this regression? So we are given B, D, K, A are the population model coefficients. So when we are doing an ANOVA or a F test to check for the significance, we are checking all of the coefficients together. So what should be is B is equal to D is equal to K is equal to A is equal to 0. So all this is equal to 0 should be our null hypothesis. And our alternate hypothesis is that at least one of them is not 0. Right. So the answer here, we are asked the null hypothesis, it will be basically, sorry, A won't be here. It will be this. So we never set the last constant to be 0. We set all the coefficients of different variables to be 0. Since we are just using these variables here to make the predictions. Right. So correct answer is here B. Okay. The next question is, which of the following is used to detect the problem of multicollinearity while performing multiple linear regression? Options are variance inflation factor, covariance, Spearman correlation coefficient, adjusted R square. It's quite straightforward. The answer here will be variance inflation factor. We did that in R. We saw how to do it. and we know if the variation in inflation factor is greater than 10, we feel that there is a possible multi-collinear relationship. Maybe the rows are not independent, the columns are not independent, and what we do is we remove a column or something. Okay. The next question is, which of the following functions is used to perform multiple linear regression in R? So core basically gives you the correlation. Mult basically is for some other thing. Confident basically gives you the confidence interval. And LM is basically what we use to perform regression, both single and multiple. So the answer here will be A, LM. Does anyone have any doubts? Great. Okay. I think so. That's the last question. Mm. If no one has any issues or any doubts, we'll stop here. But if you have any issues or if you would want me to repeat some question or some uh, explanation or some part of the code, you can tell now. We'll wait for 5-10 minutes. If no one has any issues, we'll stop the class here. Is that fine for everyone? Okay. Okay, thank you, everyone. We'll stop here. We'll continue in the next class. If anyone has any questions, please post them in the discussion forum. Feel free to post all your doubts and everything regarding exams and anything else in the discussion forum. We'll be meeting in the next week where we'll talk about week 6 lectures. Okay, thank you.